Okay, I believe that last class I did a couple of examples, and what we are getting into here is the incredibly important concept of the free body diagram. This is the core of things. It's a way of looking at the world. And by free, I mean when you look at an object, you try to figure out exactly what forces are being exerted on the object. Not the forces that it is exerting on its environment. The net force on an object is the sum of all the forces on it. It's very, very important to make sure that you look at the things that are on it. Okay? Now, there's a nice problem done here in the text, which is example 4-6. I'm going to do that problem just with some different numbers, just to look at it a different way. And that is, for instance, let's take a look at an object sitting on an object sitting on a table. Okay? Now, when we look at this, we'll call the top one M1, the bottom one M2. You must use, when you have several objects, different variables. And sometimes the text will do this, and they do it on this one, which is why I kind of don't like it many times. No, they didn't do it this time. It's okay to use MA and MB and MC. It's a bad idea to try and use little m and big M. I don't know about you, but the way that I draw a little m and a big M, they look the same, and I get thoroughly confused. So use letters, use numbers somehow to distinguish them. One thing we have to get into our heads is the concept of a normal force. This is a bit of a misnomer because people aren't used to it. Normal means perpendicular to. Mathematically, perpendicular to. Normal doesn't mean abnormal versus normal. That's not what we mean here. Normal means perpendicular to a surface. So that if I have this mouse and we have a surface, the normal component of the force, we often call it the normal force, but it really means the normal component of the force. Imagine that you are a microbe sitting on the surface of this, and you build a little house and you put up a flagpole. The flagpole is normal to the surface. So on this surface, if you build a house on the side here, this is the normal to the surface. Here it's this way. Here it's this way. Here it would be this way, and so forth. It means, imagine you are shrunk down onto the surface and you put a flagpole up. That is the normal vector. That's a normal force. Okay? Then there's a force that is parallel to the surface. We are going to see that typically, but not always, that is friction. But sometimes it might be a glue force, and so on and so forth. So normal means the force perpendicular to. Now, in a problem such as this is nothing. In fact, what I'm going to do is I'm going to set this problem up, and then we're going to take this and say, what happens if it's accelerating? It's one thing to say, we've got a book and we've got a calculator sitting on top of the book. It's another to take those same things, put them in an elevator, and accelerate the elevator. The problem changes. By the way, while I'm thinking of it, when we were talking about the normal force, if we have two objects and we want the normal force, a scale, if you put a scale in between the two objects, if you put a scale in between the two objects, the scale will read the normal force. Now, if I stand on a scale in outer space, the scale is going to read 0, but if I'm in an accelerated environment in outer space away from any gravity, then the scale may very well read something else. So the scale doesn't always read your weight either. Don't get caught with that. All right. The procedure for doing these problems is not to go and hunt through the chapter and try and find something that looks like it and then find an equation that looks like it and stuff some numbers in and get an answer. No. You're learning how to set up the problem. What we want to do here, the question is, find all the forces on all the objects. Now, we've also got the table here. Okay, we've got the table. So we could also ask for all the forces on the table. Well, we can't find all the forces on the table because the table is sitting on the floor way down there, and then we would have to find the forces on the floor, and then we'd have to find the force underneath the linoleum. I mean, where do you stop? So we'll just stop at this point here. What are the truisms? You apply or you draw a free body diagram, but you have to have as many free body diagrams as you have objects. Now, we're not going to count the table as an object again because we can't consider all the other forces on it. But we do have M1 and M2. That's two objects. We are going to need two free body diagrams. So the first thing you do is you draw the free body diagrams. We are going to assume, for the moment, and this is a huge simplification, but don't worry, we will change it, that the books are point masses. They're just dots. And what this says is, we don't care where the force is applied. Not yet. Later on, where the force is applied will make a difference. But at this point, we don't care. We just want the force. So, two objects, two free body diagrams. There's M1. That's all we got to do to represent it. Okay, a dot. Now, when you draw the forces on the object, we typically draw them emanating from the object, just for convenience. So, what is one force acting on M1 because it's here on the surface of the Earth? What's one force? Gravity. What is the magnitude of the force of gravity? What's its weight? Easily. What's the formula for the weight of an object? W is equal to mg. So, the force of gravity is down. Now, we could draw this. We could draw the force of gravity like that. But generally, just to keep it clean, we draw it emanating from it. Your free body diagram must accurately show the direction of the force. It must show the direction. It's down. And we know, don't write mg. It's not mg, it's m1 times g. Because we've got a second one here. We've got to use different variables. Thou shalt not use the same variable in the same problem to represent different quantities. Guaranteed to result in failure. Okay. What else is there? Is it John?
Yeah.
What else is there? Speak real loud too.
You have the force coming up from M2.
Okay. Now, it's up, and I will say that this is the force on the first object exerted by the second. When I write F and 2 subscript, it's on by. F on by, on by, on by. Is that it? I think so. What I do, I think of it this way. When you go to draw the free body diagram, be myopic. You look at it like this. And when I look at this, I see this touching that. That's that. I know gravity's pulling it down. The table is not touching that. See that? The table is not touching M1. There's no table force on M1. Only the forces that are actually acting on it. All right? F, B, D for number 2. All right, now I myopically look at this. John, what's one force acting on M2?
It would be
The obvious one to start with.
well, that's 2 gravity.
Yes, there's downwards, and there's an M2 times G. What else is there? Anybody else? Give me another force. Yeah, first name again?
Bradley.
Brad, right? Vincent? Yeah, Brad. Loud.
The table.
The,
Forcing up.
the table is pushing up. Now, we could call this M3, but I think it's sufficient to say that there's a force table. Is that okay? All right? Force table. You could also call that Fn, the normal force, but I'm going to call it force table. Are we done?
No.
No. What else is there?
M1 is forcing back down.
I don't want you to say that yet.
Okay.
Not yet. There is a force. You haven't proven that that force is M1G yet. But there is a force that M1 is exerting on M2. What you're doing is you're jumping a little bit ahead of the game. There is a force, and since it's straight down, you can just move it over. You can just move it over, and there is a force on the second object exerted by the first. Everybody see that? M1 is exerting a force downwards on M2. Why couldn't it be sideways? Why couldn't that force be canted sideways? Let me ask this first. What is the acceleration of everything? What is the acceleration of every object? Is anybody moving? No. Is anybody starting to move? No. So what is the acceleration of the first object? What's the acceleration of the second object? 0. And of course the table is not accelerated either. So can any of these forces, can there be a single one that's pointing to the left or the right? No. The net force horizontally is 0. If this were pointed this way, this one would have to be pointed the other way or whatever. But as you can tell, they're just going to be straight up and straight down. So you draw the picture. It doesn't hurt to try and write the accelerations in a problem like this. We write the free body diagrams. And there's no reason you couldn't put this one here and put that one there, as long as they're parallel and they're both straight down. The purpose of the free body diagrams is for you to see and visualize the forces that are going on. That's why you are doing this, so you can see what's going on. Once you have the free body diagrams, now you apply Newton's laws of motion in both horizontal and vertical directions to obtain mathematical equations that hopefully you can solve. So the procedure is draw the diagrams, label things, make a drawing, draw the free body diagrams, then use the free body diagrams to apply Newton's second and third law of motion to each object to hopefully get a set of equations that you can solve. Now, if I look in the horizontal direction, do any of these forces have horizontal components? Nah. There's nothing going on in the x direction. So we're done. We only have to look in the vertical direction, but in some problems you do have to look in both directions. So we come to here and we say, first object. The sum of all the forces on the first object, the sum of all the forces on the first object from other objects, okay, is equal to the mass of that object times its acceleration. What the heck, I'll write it in. But while we're going here, what is A1? What did we decide A1 was? 0. But it doesn't hurt to write it out just to make sure you didn't forget it. Now, this means sigma. Sum. This means list all the components of the forces that are acting on the first object. That's what the free body diagram is for. Okay? Now we're looking in the vertical direction, and we better assign a coordinate system. So we will use up is positive and down is minus. It doesn't make any difference as long as you stick to your guns. What is the component of this force? Now it's aligned with the axis, so it is either plus or minus the magnitude. And since it's pointing along the plus direction, is this plus or minus? Plus. Okay, what about the gravitational force? It too is parallel to the chosen axis. So it is m1g, but does it have a positive or a negative component? Negative. So here's an equation. 0 is equal to F12 minus m1g, and therefore, moving the m1g over, we just proved what you wanted to say. We just showed that the force on 1 exerted by 2 is equal to the weight of the first object. Some people might have wanted to go right to this, but it turns out that if this were in an elevator accelerated, this would not be true. This would not be true. This is only true if everything is sitting still, see? So you got to be careful. Don't make assumptions. Prove everything. All right, but so we just solved that. We assume that M1 and M2 are given. I could say, suppose M1 was 1 kilogram and M2 was 5 kilograms, for instance. So we know this now. This would be equal to, what did I say, 1 kilogram times 9.8 meters per second squared is 9.8 newtons is F12. So we have found one of the forces. You probably knew that just off the top of your head, but it doesn't, we just proved it. Any questions so far? Now, we have to apply Newton's laws of motion to the second object. Again, nothing's going on in X, so I'm going to come over here, object number 2. The sum of all the forces on object 2, exerted by all the other objects, is equal to m2 times its acceleration. But what's A2? 0. Okay? Equals. This means list all the components of the forces that are acting on object 2. List all the forces now over here. You can list them over here if you want. Go the other way. All right. Ft is the component of that. Now Now it's lined up with the axis. Is it plus or minus Ft? It's a plus Ft. All right. What about gravity? Positive or negative? Negative. Minus m2g. And what about this force? Minus. So from this, now this is 0 is equal to this. There's an equation. I'll write it out like this just so everybody can see it. Therefore, the force exerted upwards by the table is m2g plus F21. Now we can find m2g. Uh-oh. What's F21? How do we find that? See, this is where oftentimes the textbook, we just do this automatically, but we forget what we're really doing. What's F21?
Force exerted downward by M1 on it.
But can we figure out a value for it? What of Newton's laws have we not used? We used the second law. What about the third law? The third law says, the third law is out there. The third law says that the magnitude of these two forces are the same. These two forces have equal magnitudes. This force is pushing up by the same amount this one is pushing down. That's the third law. So you apply the third law of motion, and this is equal to, which says that we can switch these two indices around. We can switch them. And this is 5 kilograms times G plus 9.8 newtons. You get your calculator out and do that. 5 times 9.8 is 20, whoops, 5 times 9.8 is 49 newtons plus 9.8 is 58.8 newtons. But we can see something else, that F12 is F2, F12 is M1G, and so you could also write this like this. So it says the table is pushing up at M2G plus M1G. In other words, it's pushing up with the total weight of these two objects, which is what you would expect. That is exactly what you would expect. But this shows how the third law comes in, and you might say, how does the table know that other one is up there? How does the table know that gravity is up there? It's because the force is transmitted through this, and it's through this relationship right here that we get down to the final answer. Now, what would happen if this were in an elevator? How would this whole problem change if I said this is in an elevator moving up at constant velocity? It wouldn't change. Why? All of these would still be 0. All of these doesn't make any. The elevator could be moving up at 100 miles an hour. It doesn't change. But what if the elevator accelerates upwards? Then these are not 0. They are not 0. And then all of this would change. This would change. By the way, if they're sitting on each other, how would these be related to each other? If they were all sitting in an elevator now, different problem, and the elevator is accelerating upwards, how must A1 and A2 be related if they're touching each other? They would have to be the same. See? They would have to be the same. Let's do an elevator problem, but with just one object, okay? With just one object. Anybody have any questions, though? Yeah. If you got a question, answer, because if you got a question, I guarantee you somebody else up there's got the same question. And you're not holding this up at all. Okay, let's do an elevator. Okay. Or I think as the text does it, let's do 4-7. Let's do example 4-7. It's an accelerated problem. What we've got here is a box, always the box, the mystery box. We've got a box. A person pulls upwards on the box with a force greater than the box weight. For example, in this case, the box has a mass of 10 kilograms. We've got a 10 kilogram box. It's got an upwards force on it, and in this case, this is 100 newtons. F pull is 100 newtons. Just 100 newtons. All right. And the question is, what's the acceleration? What's the acceleration? Okay. Is it going up or going down? We'll have to see. It could be going down. It could be going down. Don't assume it's going up. It could be going down. I can be holding on to something and lowering it. Okay? It could be going down. Don't assume it's going up. But that doesn't make any difference. What is A? How many objects? So we draw the free body diagram first. There's the object. And one force on it is this one. And what else is acting on it? Gravity. Of magnitude mg. Let's calculate it. M is how much? 10 kilograms. Okay? So there is a force of 100 newtons going up and a force of 98 newtons going down. We've got the free body diagram. There's one object, one free body diagram. We already calculated what the weight is. Now we apply Newton's laws. Turns out in this one, the third law is not going to do anything. But the sum of all the forces in the y direction on this object, let's again take up being plus, is equal to m a sub y. And now, we look at this, we've got this one going up. Is it a positive or negative component? It's positive. It's lined up, it's parallel to the axis, so it's 100 newtons, but it's in the positive direction, so it's plus. Gravity is parallel to it and downwards, minus 98 newtons. So ma sub y is equal to 2 newtons. So the y acceleration is 2 newtons divided by the mass, which is 2. Now watch how I do the units, and this is what you're supposed to do too. This is 2 kilogram meters per second squared. And then the mass is 10 kilograms. Kilograms cancel, and we get 0.2 meters per second squared. Okay? Yes. Does this necessarily mean it's moving upwards? Not necessarily. You could have a situation where it goes like that. It could be moving downwards with a rocket engine upwards, and it's coming down, and then in either case, the acceleration is upwards, but the velocity could be either way. We didn't say how it would start out or anything. Though, if you just had it hanging there and turned and started pulling, then it would move upwards. What would the tension be if the acceleration were zero? Well, actually, now let's not look at that, okay? Let's not look at that. Actually, what would the pulling force have to be so it just was balanced? Well, then it would be, there's a 98 Newton force down. If we drop this to 98 newtons, then it would not be accelerated at all. All right, questions or comments? Draw the picture, choose a coordinate system, draw the free body diagram, apply Newton's equations of motion, and finally solve the equations that you get. Let us do example 4-11. Okay, let's see. Again, a box. I think it's 10 kilograms again, but what the heck. Example 4-11. Now in this case, we've got a box sitting on the ground. Let's make sure we get it right. Okay, it says the smooth surface of the table. And what they're telling you here, folks, is that there's no friction. This thing is on an air table. This is an air track. This is on our air track that we saw. The air track is level. It's sitting there, but we're going to pull up with 40 newtons at 30 degrees. So we're going to pull up with a force 40 newtons at 30 degrees. Like that. And the question is, what is the acceleration of the box? And the normal force. Let's find that too. When you say there is no friction, listen carefully. We'll get into friction here quite a bit. No friction means that if I had this sitting on the table on the air track, think about this, we go to our air track, and the box is sitting there, what would happen if I move the air track? There's no friction if I move the air track exactly sideways. Will the box do, would the glider do anything at all? No, it would just sit there. It would just sit there. Because no friction means you can't apply a force this way. But if I took the air track and went like this, would that change the glider? Oh yeah. But if I move the air track sideways, the glider would just sit there with the air track moving underneath it. As long as there's no friction. Okay. And this box, I do believe, is 10 kilograms again. Why not, you know? All right. What is the acceleration of the box and the normal force? We got the picture. Let's choose a coordinate system. Whenever I draw in the x or the y, that indicates the positive direction. Now we draw the free body diagram. There's the box. Now the table must be pushing straight up. So, do they use Fn? Yeah, they say Fn. Okay. We call it Ft, Fn, whatever. Gravity is pulling it down. And then we must reasonably accurately draw in the other force. This is this way, 40 newtons at an angle upwards of 30 degrees. So the free body diagram are those three vectors. One straight up, one straight down, and one angled up 30 degrees above the plus x-axis. Only one body here, so we only have one free body diagram. Now we apply Newton's laws of motion. In the x and in the y direction. Now we can't just do one direction. So we have the sum of all the forces in the x direction must equal m times the acceleration in the x direction, which is not 0. And unlike some of you tried to make in the exam, it's not 9.8 meters per second squared. Okay? There's a tendency, if we don't know what the acceleration is, to make it 9.8 meters per second squared. Now, only if it's in free fall. All right? All right? Does the normal force have an x component? Is there any tendency of the normal force left or right? Nope. What about gravity? Nope. What about the pulling force? Yes. We have to find this component. That's the x component. This is the y component. This is the adjacent side. This is the opposite side. So this is, by inspection, positive. It is the adjacent side, so it is 40 newtons. And what goes with the adjacent side? Which trig function? Cosine. You need to know that, like cosine of 30 degrees. Divide both sides by m. A sub x is 40 newtons cosine 30 degrees divided by the mass. So this is 40 newtons cosine 30 degrees divided by 10 kilograms, and that gives us the answer, which is 3.46 meters per second squared. So we've got that. What about the y component of the acceleration? If it stays on the table, this is where you got to think about it. If it stays on the table, does it ever move upwards or downwards? No. And if it never moves up, first name again? Sarah. If it never moves upwards or downwards, what's the y acceleration? 0. Okay? Sarah, are we making an assumption there? How do you know it stays on the table? What would happen if you pulled on this with a force of 50,000 newtons? I mean, what's going to happen? It would fly off the table, and then is this the correct free body diagram? No. Because if it flies off the table, what's the table force? 0. We're making an assumption here, folks. We're making an assumption. I chose a really huge figure because you said, oh yeah, it's going to come off the table with 50,000 newtons. We're making the assumption that it says in the table. So now we apply all the forces in the y direction, and that's ma sub y. We know that's going to be 0, kind of. And so now we have, is gravity downwards, or is the force of gravity, which by the way is, I'm just going to jump to it, it's 98 newtons, okay? Is that a positive or negative component? Which way is it? It's negative. So we have a negative mg, and then what else do we have? The normal force. Is it a positive or negative component? Positive. And then the component of this, is it positive or negative? It is positive, plus 40 newtons. This is the opposite side, that is the sine of 30 degrees. And this allows us, this tells us that the normal force is the weight of the object less this amount this turns out to be 98 newtons, and I believe the other one turns out to be, or let's see, is this a 10 kilogram box? Yeah. Okay. And in this case, it is 20 newtons, because the sine of 30 is 0.5, is 78 newtons. So the table pushes up with a force less than the weight of the object. The normal force is not equal to the weight of the object. Some people always want to say that. No, it's not. So Sarah, let me ask this. I keep increasing this force. And of course, that means this is going to get bigger and bigger and bigger. I'm not going to worry about that. What is the condition? What will the normal force be when it's just ready to leap off the table? Which means I could take the table away and it would still behave the same. It would be really strange. Would there be any normal force? No. So if you set this equal to 0 and calculate what force here will make that 0, that is as hard as you can pull on it and still have it stay on the table. It's a really bizarre situation, but you could, if you pulled it just right, I could never do it. I could pull it so that it would move like this through the air, like that. Where this is a rocket engine, pushing it, it would move it would be weird looking, really, really strange looking. Okay, let's stop right there, and we'll come back now, and we'll take a look at the Atwood's machine, which is the double elevator on page 91, and the two boxes hooked together with a cord. But we need to get going on some problems. Now I assigned 1, 2, 3, and what?
7.
And 7. Okay. Let us do 10, 11, 12, and 14. 10, 11, so this is 4-10, 4-11, 4-12, and 4-14. For you folks, this will be due on Friday. And for our video folks, these will be due on Monday. All right? All right, it's a nice day out there. Get out there and enjoy it while you can.